Hello everyone. I'm going to introduce an article whose title is Improved Prediction of Swimming Talent Through Random Forest Analysis of Anthropometric and Physiological Phenotypes. Introduction and Background. Talent Identification, TID, and Talent Development, TED, programs have been crucial in identifying and nurturing athletes, with anthropometric and physiological traits serving as key indicators of talent, especially in swimming. However, existing studies often rely on cross-sectional analyses, focusing on specific ages or events. This approach can lead to unreliable results due to performance variations across different age groups. To address these limitations, this study utilized longitudinal data to create a more accurate and reliable talent identification framework for competitive swimming. Specifically, the researchers developed a machine learning-based model to predict athletic talent in adolescent swimmers, using anthropometric and physiological data. This model not only provides deeper insights into talent identification but also enhances decision-making in athlete selection and development. Results. Baseline data were collected from 5,444 participants aged 10 to 18 in Shanghai, 3,268 for males, 2,176 for females in total. The independent test data applied to the talent prediction model was collected in Shandong, 66 for males, 52 for females, aged 10 to 18. The prediction models were built based on the Shanghai data as shown in the figure. First, 30% of the data, adjusted for the covariates of age and sex, was randomly set aside as the preserved test dataset for model validation, while the remaining 70% was used for model building. Based on the 3-year follow-up records, athletes were classified into two groups. Those who ranked in the top 8 in national-level competitions during the follow-up period were designated as PHLAs, and the rest as PAs. Initially, a set of 18 anthropometric and 4 physiological phenotypes were collected as independent variables. These were then refined using the lasso method to determine the final feature set. For hyperparameter tuning, 5-fold cross-validation was employed. 9 different machine learning algorithms: random forest, support vector machine, logistic regression, decision tree, multilayer perceptron, ADA boost, gradient boosting, voting classifier, and k-nearest neighbor were trained on these variables. The best performing models were selected based on a range of performance indicators, including AUC, accuracy, sensitivity, specificity, PPV, NPV, and F1 score. Model implementation was carried out utilizing Python packages NumPy, Pandas, and scikit-learn. To address class imbalances within the dataset, a naive random oversampling technique was employed, wherein instances of the minority class were duplicated to even out class representation. Furthermore, the impact and relevance of the selected features were assessed using SHAP values with the SHAP Python package. We compared the phenotypes of PHLAs and PAs aged 10 to 18 to seek useful information for talent identification. The analysis identified unique patterns in age-dependent development tendencies, prompting a classification of athletic phenotypes into categories as shown in the figure. In categories A and B above, the phrase in general implied the feature for PHLAs had higher-lower values in at least 6 of the 9 age points. From Figure 2 and Figure S2, we noted the differences between males and females, as well as between PHLAs and PAs across all the age studied. Specifically, males consistently achieved higher values in most phenotypes compared to females in those with exception of skin folds, thigh circumference, and pelvis circumference. In addition, most of the phenotypes for male PHLAs were higher than those for male PAs across all ages. Different from males, most of phenotypes in females focused on category B and C, although skinfold measurements showed consistent trends across both sexes. As mentioned earlier, anthropometric and physiological traits showed age and sex-dependent differences. After adjusting for age and sex, the dataset was split 70-30 for training and testing. Using lasso regression, we identified 14 key phenotypes associated with athletic talent, including 10 anthropometric indicators, e.g., height, abdominal skinfold, chest circumference, and 4 physiological indicators, e.g., hemoglobin, lung capacity. The optimal penalty parameter was log, lambda, equals -5.2, minimizing predictive error. Among the 9 tested models, Random Forest, RF, achieved the best performance, with an AUC of 0.9860, 94.14% accuracy, and an F1 score of 0.9432. As a result, the RF-based model, RF 10-18, was selected for further analysis due to its superior predictive performance. Discussion and conclusion. This study has several strengths. Firstly, it covers a large population base and a wide age range, ensuring reliable data and broad applicability for the constructed model. Secondly, it improves on previous cross-sectional approaches by incorporating a 3-year follow-up, providing the predictive model with foundational insights into the future talent potential. Nonetheless, the research has limitations. Predominantly, it draws upon anthropometric and physiological indicators, indicating the need for further diversification of data dimensions in future research. Moreover, despite validating the constructed model against the Shandong dataset, the small sample size underscores the urgency for subsequent validation within larger and geographically varied cohorts. In summary, this study has constructed a well-validated talent prediction model using anthropometric and physiological indicators through the random forest algorithm, which is applicable to swimmers aged 10 to 18 years old. That's all, thank you.